reactor, but also how to determine the required coolant flow and the area that is needed for heat exchange. Let us consider a continuous stirred tank reactor in which the reactant A is converted into product P. Remember that if the reactor is ideally mixed, the product and remaining reactant that are leaving the tank are at the same concentration as the concentrations inside the reactor medium. It is an exothermic reaction, and that means that heat is generated. The joules that are generated in this reaction can be calculated. To do that, you need to sum up the total enthalpy of the products and subtract the sum up of the total enthalpy of the reactants involved in the reaction. So here we have 1 mole of reactant producing 1 mole of product. So 1 mole of product multiplied by its combustion enthalpy minus 1 mole of reactant A multiplied by the combustion enthalpy of the reactant gives the heat that is generated. The values for these combustion enthalpies can be found in chemical data books, but make sure that you convert them in joules per mole if they are provided, for instance, in joules per kilogram. Not only check the units, but also check at which reference state these combustion enthalpies were measured. The standard heat of combustion is associated to the combustion of the reactants and the products at standard conditions, usually 25 degrees Celsius and 1 atmosphere. If the actual temperature is much higher than the reference temperature, the reaction enthalpy may not be the same as the standard heat of reaction calculated using the standard heat of the combustion data. In this case, you need to take into account that the enthalpy change needed to get the reactant and products at the elevated temperatures. If your reaction occurs at slightly higher temperature, there's no problem. The enthalpy of the reaction will not be different too much. So now you calculated the reaction, the heat of reaction, and now we can set up the enthalpy balance for a tank. This tells that there is a change of enthalpy in the tank. Enthalpy enters the tank via the flow in and leaves via the flow out. However, there is also this increase in enthalpy due to the heat that is released in the exothermic reaction. So the content of the tank will get hot. The specific enthalpy of the flow in, H in, and the flow out, H out, can be calculated from the specific heat capacity of the flows and the temperature difference between the temperature of the incoming stream and a reference temperature. You may wonder why this reference temperature. Well, realize that the specific enthalpy as such cannot be measured in absolute terms. You can only measure a relative change in enthalpy, but that means that you need to define a reference state, a reference temperature, and a pressure at which the specific enthalpy is assumed to be 0. For air, a reference temperature of 0 degrees Celsius or 273 Kelvin is used, and a pressure of 1 atmosphere, so 10 to the 5th Pascal. The heat capacity of air is 1 kilojoule per Kelvin per kilogram air. So it means that we can say that the enthalpy of 1 kilogram air at 30 degrees Celsius is 30 kilojoules higher than the enthalpy at 0 degrees Celsius, so at its reference state. To remove the heat from the tank, we can install a cooling coil. The lower blue part in this drawing represents such a cooling coil. It is typically a tube through which the coolant flow, the fluid moves as a plug flow from the inlet of the coolant to the outlet. In this way, the heat that is released in the reactor tank itself is taken up. Let us set up the overall steady-state enthalpy balance. The energy that was building up is now transferred to the coolant, and the coolant will leave the cooling coil at elevated temperature. From the overall balance, we can calculate the required flow of coolant, and is the FC. The second aim was to determine the required area for the heat exchange. The area, or the length of the cooling coil, can be calculated using the enthalpy balance over the coolant phase only. The heat that is transferred over the outer area A of the cooling coil is U times A times delta T, and in which U is the overall heat transfer coefficient, and delta T stands for the temperature difference between the hot content of the tank and the temperature of the coolant at the other side. The overall heat transfer coefficient is a measure of the resistance to the heat transfer. This resistance not only depends on the thickness of the wall of the tube and the material that the tube is made of. It also depends on the heat transfer coefficients inside and outside the cooling coil. Since the temperature of the coolant differs over the length of the coil, we need to use the logarithmic mean temperature difference to calculate the required area. So we take the temperature difference in the tank at the outlets, delta T2, minus the temperature difference in the tank at the site where the coolant enters, delta T1, and divide that by the natural logarithm of delta T2 divided by delta T1. You would maybe expect that delta T1 is the temperature of the coolant that enters minus the temperature of the feed that comes in, but that's not the case. Due to the ideal mixing, the temperature in the feed stream of the tank is the same at all places, and that means also at the outlets. So the delta T1 is your T of the coolant in minus the TF out due to that ideal mixing. So within this module, you learned how to calculate the amount of energy that is generated in a reactor, in a reaction. You're able to calculate the required coolant flow, and you're able to calculate the required surface area of the cooling coil, so that the heat that is generated can be taken away from the tank. Good luck, and see you back soon.